Okay, good morning, I guess good afternoon, good evening. It just depends on where you're at and what you're doing right now. What we're going to talk about today is the angle measures of polygons and what is the relationship between the angle measures of triangles and other polygons. Well, if we do a little flashback here, we have been working with triangles for a while, and we know that the internal angles of a triangle we have learned total 180 degrees. So in this case, this angle measures of a triangle says, what is the measure of angle C? So we're trying to figure out what in the heck that is, but we know, that angle A plus angle B plus angle C is going to equal 180 degrees. And if we know that angle A is 54 degrees, we have angle B is going to be 85 degrees plus, of course, angle C equals 180. These two added together will be 139 plus angle C equals 180 minus 139 from both sides. And we find out that angle C is actually going to be 41 degrees. Now, you may not need to go through all of that math to figure this out, but I want to make sure you see how did we come about it. It just wasn't magic. So there we go. This angle right here is 41 degrees. So with that, we can see that once we have this first triangle, we're going to be able to build on that as we look at the internal angles of the remainder of these polygons, and there'll be a system to it and a way that we can calculate that. And what we find out, let's see. So we have polygons. Polygons are closed figures formed from 3 or more line segments such that each segment intersects exactly 2 other segments. One at each end, and no segments with a common endpoint are collinear. Well, let's see, let's break some of this stuff down. Closed figure. So look, we have a closed figure here where, we end up having a object. If we were to fill it in, we could fill it in because all of my points come to a closed figure. And then it says that each segment intersects 2 other segments. So here I have this segment intersects this segment and this segment. So, we have these points forming. And then it says no segments with a common endpoint are collinear. Well, they don't want to see this. They don't want to see a straight line because that is technically one side of our quadrilateral and it doesn't form an angle. So that's where they're going with that. So as we can see here, we have this is considered a convex polygon for every line segment connecting to the other 2. There are no points inside the polygon. And then this would be a concave image. And I like to think of it that this right here sort of forms a cave, cave opening where they're not all going outward. We have an internal angle. This would be that angle going inside the polygon. So knowing that, let's see, as we look forward, we have here the polygon interior angle sum theorem. What it tells us is that the sum of the measures of the interior angles of a n-gon is this, right here. The sum of the measures of the interior angles of an n-gon is 180 times n minus 2 degrees, where n is the number of sides. And we use reference n in math, and this is just intended to be some future number. N is some future number that we decide. Now, we may decide that it has 5 sides, 10 sides, 1 million sides. That is to be determined later on depending on how we use or what kind of object, what kind of polygon we're using. So just n is going to be that variable, that unknown that we're going to look for, some future number. And so we have, of course, that equation, which is 180 times the number of sides minus 2 degrees. That's going to give us the sum of the interior angles. So as I look here, I have this pentagon. I have a pentagon which has 5 sides. 1, 2, 3, 4, 5 sides. And what are the sum of the measures of the interior angles of the polygon? Well, I could divide this thing up. I could say, hey, if I were to draw some triangles on the inside of it, I could say, well, that's 180 degrees because we knew a triangle was 180 degrees. That's 180 degrees, and that's 180 degrees. And if I add that together, 180 times 3 is going to give me 540 degrees. Now, this may not be always the perfect method of doing it, but we can use our formula. So if we look here, our formula, the sum, what is the sum of the measures of the interior angles? Well, I have 180 degrees times n minus 2 degrees is going to be the sum. And n, remember, n is the number of sides. So when it has a pentagon, we have 5 sides. Now, so when I look at that 5 sides, I replace n with 5. I end up with 180 times 5 minus 2 degrees is going to be 180 times 3, which is 540 degrees. So there you have it. This way I just sort of created some triangles and added my internal angles up. That's fine if it's a small object, but as it starts to get larger, we need to understand that it could get too difficult to draw these triangles and add that. So using our formula is always going to be a much easier process. So, or it very likely is a much easier process. So there we go. The internal angles of a pentagon, a 5-sided polygon, is going to be 540 degrees. Let's see, so as we go on, here's an example, and let's see, we have, how many, it says, what is the measure of angle K? Right here. What in the heck is that degree there? And I know that I could figure out all my internal angles. See, I have 90 degrees here. I am missing that one angle, but I know that I have a 1, 2, 3, 4, 5, a 6-sided object. So now if I were to use my formula, I have 180 degrees, times n minus 2 is going to give me the value of my internal angles. So my internal sum, internal sum, right? So I have 180 times 6 sides minus 2 is equal to 180 times 4, which is going to be 720 degrees. So I know that all of these should add up to 720. So if I go ahead and make that into a formula, I have, let's see, I have x plus 107 plus 90 degrees plus 154 plus 115 plus 106 should all add up to 720 degrees. So when I combine like terms, right, I'm going to go ahead and just combine all my numbers, and I have x plus 572 is equal to 720. I'm going to go ahead and do my inverse operations to isolate my variable. And it turns out that x is going to be equal to 148, which in this case was angle K. So angle K is going to equal 148 degrees, right there. So we were able to use that formula, finding out some information to identify that unknown value. And there you go, there's a good example of practicing that. Now with using the internal angle sum theorem, what we're going to find out is we're going to start talking about regular polygons. So as we talk about regular polygons are both equilateral and equal angular, which means that my sides are all congruent, okay? My sides are all congruent, and equal angular means that my angles, my actually, my angles, interior angles, are congruent, and then therefore my exterior angles will be congruent. So that's my equal angular. So finding the sum of interior angles. Let's see, we just did a minute ago, and we said that, hey, the internal angles of a pentagon are 540 degrees. So when we add those all together, it came up to 540 degrees. But what we want to find out is, what in the heck is just one of those angles? Well, if you think I have, all of these are going to be congruent. So I have 5 congruent angles. So I have the sum, which was, we said 180 times 5 minus 2 equals 540 degrees. And then in order to find out how much each one of them is, I take that 540 degrees and I divide it by the number of sides, which is 5 sides. I divide it by 5 sides. And that's going to look something along the lines of 540 divided by 5. And we find out that each one of those angles is going to be 108 degrees. Each interior angle is 108 degrees. X equals 108 degrees. So that's how we would find the sums of that's how we would find one of the interior angles of a regular polygon. Let's see here, looking at example number 2, it says, how can you best describe the cells of a honeycomb using polygons? Well, if I look here, each one of these cells, fascinating enough, I still raise bees. I have beehives on my property, and they are fascinating little engineers, but they create honeycombs which are 6-sided, and they are hexagons. So 6 sides, hexagons. So they look like hexagons, and that means that we have 6 sides. And then what else could we be able to figure out about that? Let's see, I know that the internal angles of that hexagon or that honeycomb would be 180 times n minus 2, which in this case n is 6 sides. So I have 180 times 6 minus 2 is equal to 180 times 4, which is 720 degrees. So that's the sum of the internal angles. And if I wanted to find out what the each individual angle is going to be, I could turn around and just say, okay, well, I got 720 degrees divided by 6 sides is going to give me 120 degrees each. So the sum of these would be 720 degrees, but this angle right here is simply going to be 120 degrees. And that's some math describing the honeycomb of a honeycomb. Now continuing on with another example here. It says the internal angle of a regular polygon has a measure of 140 degrees. What type of polygon is it? So now we are combining the internal angle now we're using the internal angle to turn around and try and figure out what kind of polygon we have. So what we have here is we know that something is going to equal 140 degrees. And I know that I could find the entire sum of the interior angles by using our formula, 180 times n minus 2. And then we learn that that sum divided by the number of sides is going to give me the internal angle. So what I can do is I can just divide this side by the number of sides, and those two, that's how I would find one internal angle. So now I would, in order to isolate my variables, I need to get rid of, reverse some order of operations here. So I'm going to multiply both sides by 1 to where I can get my, n, so I can get my in the numerator, the variable in the numerator. And let's see here what happens. N divided by n becomes 1. And then I end up with 180 times n minus 2 is equal to 140n. Then I have 180n using the distributive property here now, right? 180n minus 360 is equal to 140n. I'm going to add 360 to both sides. 180n is equal to 140n plus 360. I'm going to subtract 140n. And it turns out that, bring it up here, ran out of room, 40n is equal to 360. Divide both sides by the coefficient of 40, and n is going to be equal to, okay, it does not equal 90, it equals 9. So right here, let me erase that. So n equals 9, so that is, what type of polygon is it? It is a polygon with 9 sides, which is a nonagon. Let's see, non-gon. Right there, 9-sided polygon. Continuing on, as we talk about the external angles now of a polygon, we find out that the external angles, an external angle of a polygon is an angle formed by a side of a polygon and an extension of the adjacent side. An extension of the adjacent side. So in essence, we have the external angle is this thing right here. So the internal angle, we take the side of the polygon and we would extend it out, and then that creates an external angle, this angle which is outside, right? It's outside the polygon, so that's where it is. And just thinking about it, we know that if it did extend to a straight line right here, that total should be 180 degrees. You know, it's a straight line, it's a linear pair, these two angles, so my inside angle and my outside angle would form 180 degrees, or sum to 180 degrees. So using that with some information, as we go through here, it says the polygon exterior angle sum theorem is the sum of the sum of the measures of the exterior angles of a convex polygon is going to be 360 degrees. And we're going to prove that here. Okay, so the sum of the measures of the exterior angles of a convex polygon is 360 degrees. This will be a regular, or well, I guess it's any polygon, but so again, convex means all my angles are going outward, no inside angles inside the polygon. So as we look at this, let's see, we could say that we did learn again that the interior angles of a pentagon came up to 540 degrees. So in 540 degrees, we said 540 degrees divided by 5. It turned out that the internal angles were 108 degrees. So let's go ahead and park that information. We're going to come back to it, and we're going to go ahead and talk about those exterior angle sum theorems. So it's telling us that the exterior angles, are going to sum to 360 degrees. Well, in case of this polygon, I have 5, exterior angles. So my 5 exterior angles are going to equal 360 degrees. If I wanted to find out what does one of those exterior angles equal, I could divide by 5, and that would simply say that my exterior angle is going to be equal to 360 divided by 5, which is 72 degrees. And let's see here, if I said that this exterior angle was 72 degrees, sure enough, 108 plus 72 is equal to 180 degrees, which is talking about this linear pair. And which is talking about this linear pair. So the interior and the exterior angle are supplementary to each other. Add them together, they form 180 degrees. So that is using that or looking at that exterior sum theorem. So let's go ahead and knock some examples out here. And it says, what is the unknown angle measurement and what is the value of x? Okay, well, in the exterior angle sum theorem right here, we said that all of these angles, all of my exterior angles of a convex polygon will add up to be 360 degrees. So I know that they're going to equal 360 degrees, and let's just start filling in some of those angle measurements. I have 360 is equal to 90 plus 72 plus x plus 7 plus 96 plus 82. So I've taken all of those measurements, right, and I'm going to add them together, make them total 360 degrees. When I combine like terms, you know, I can combine all my numbers over here, and I'm going to get 360 degrees is equal to x plus 347. I'm going to subtract 347 from both sides. And I find out that x is going to equal 13. Now, so I found the value of x. What is the value of x? X is 13. Well, when I go over here and I plug it into this angle measurement, right, x plus 7 degrees is equal to 13 plus 7, which is 20. So that missing angle measurement is going to be 20 degrees. And there we go. We were using some of the information that we're learning here to work through some examples. I'm going to gloss over example number 4, and I'm going to come back to it because really what we have here is sort of a duplicate problem. Look at an example from number 4. It's talking about a decagon, and that is a 10-sided object. And again, so as we're looking here, again, I have a decagon for example number 5. So we're going to just work through 5, and I think that's going to give us the answers to example number 4. So number 5, it says, what is the sum of the interior angles of a regular decagon? Well, we know that it's going to be 10 sides. We'll start there, and I have the sum is going to be 180 degrees times n minus 2, which is 180 degrees times 10 sides minus 2, which is 180 degrees times 8, which we find out is going to be 1,440 degrees. That is the sum of the interior angles of a decagon. Now it says, what is the measure of each interior angle of a regular decagon? Well, we find out that, again, that was going to be, we take the sum and we divide it by the number of sides, and then each interior angle is going to be 144 degrees. So there we go. Now, let's take that to example number 4. So this angle right here is 144 degrees. And then what is the measurement of angle number 1? So we know that angle number 1 is equal to angle number 1 is equal to, or should I say 144 degrees plus angle number 1 is equal to 180 degrees. Subtract 144 from both sides, and angle 1 is going to be 36 degrees. So there you go. That's why I went ahead and I did example number 5 leading into example number 4. So, and we'll do this last example, number 6. We have 4 interior angles of a pentagon. Measure this. 2, 3, 4. It says, what is the measure of the final angle, final interior angle? So we have another angle out there. So when I add all those together, let's see, if we take a pentagon and we want to find out what do the interior angles measure, we would say 180 times 5 minus 2 is going to give me 540 degrees. Remember, that is the number of sides. So the internal angles add up to 544 degrees, and then we have 5 angles represented right here. So let's see, I have 156 plus 72 plus 98 plus 87 plus that unknown measurement is going to be equal to 540 degrees. Go ahead and combine like terms. So we have, when we combine like terms, we have 413 plus x is equal to 540. Subtract 413 from both sides, and x is going to be equal to 127. So that missing angle measurement is going to be 127 degrees. So there you go. We were able to talk about some of the information here. You know, we were talking about the angle measures of polygons, the internals, the external angles, how the relationship, how we associate them. And now we were able to work through a couple of examples, and we'll go back and we will do today's classwork and see how that works out and reinforce some of these theorems and mathematical practices.